my presentation outline is as follows. First, I have the introduction, followed by brief comments on the Adomi and Sugarkope bridges. The Volivo Bridge is central to the Adomi and Sugarkope bridges. Then there's an update on the Volivo Bridge project, structural elements of a cable-stayed bridge, then new materials to be incorporated in the design and construction of the Volivo Bridge, then closing remarks. Yes. So the construction of a new bridge across the Volta River on the eastern corridor of the Republic of Ghana. The government of the Republic of Ghana has received a Japanese ODA loan from JICA to finance the construction of a new bridge across the Volta River on the eastern corridor. The eastern corridor starts from Tema to Asuchari Junction, at Impoku, Asikuma Junction to Kulungu. The consultants for the design review and construction supervision are central consultants in joint venture with Oriental Consult Global of Japan and in association with Hack Consult and associated consultants. Located on the northern end of the project site is Dufo Adidome, a village in the Volta region, and on the southern end is Volivo in the eastern region. At present, there are 2 bridges crossing the Volta River south of the Akusumbu Dam. That is the Adomi and Sugarkope bridges. The Volivo Bridge, which will be between the 2 bridges, will secure shorter transport distances if for some reason one of the bridges is closed. The project site is 31 kilometers south of the Adomi Bridge and 46 kilometers north of the Sugarkope Bridge along the Volta River. And here we have a map showing the location of the relative locations of the bridges. So we have the Adomi Bridge, then 31 kilometers to Volivo Bridge, then downstream 46 kilometers to Sugarkope Bridge. The Adomi Bridge is a suspension bridge with a total span of 334 meters. Volivo will be a cable-stayed bridge with a total span of 540 meters. And the Sugarkope Bridge is a beam and slab bridge with a total span of 646 meters. This is the Adomi Bridge. It is the first permanent bridge to cross the Volta River on the National Route 2. It was commissioned by President Nkrumah on 25th January 1957. The bridge was designed by Sir William Haku and partners and William Brown of Freeman Fox. Permanent work on the bridge began in 1955 and was substantially complete by November 1956. The contractor was Dorman Long Engineering, Bridge and Engineering Limited. The Adomi Bridge is a 2-hinge lattice steel crescent-shaped arch bridge with a 2-lane road deck suspended by cables. The main span is 245 meters long, and as I said, the total span is 334 meters. Due to the high traffic loads and lack of maintenance, some serious cracks developed on the bridge deck's transverse beams in 2008. The bridge was closed to traffic in 2014, and a major rehabilitation work involving the replacement of the entire road deck and all the hangers by MCE of Austria. The newly rehabilitated bridge was opened to traffic in December 2015. This is the Sugarkope Bridge. The Sugarkope Bridge is located on the National Route N1 and connects Sugarkope to Soko over the Volta River. The Sugarkope Bridge is a multi-web T-beam bridge made from pre-stressed and reinforced concrete and was built by 2 German contractors, A.H. Eibau and Held and Franke, between January 1965 and January 1967. It is the longest bridge in Ghana with a total span of 646 meters. That is 17 spans of 38 meters each. A major rehabilitation of the bridge took place during the period between 1995 and 1997, and it involved the strengthening of the substructure with the introduction of 4 cast-in-place piles at each pier location. Now the Volivo Bridge. That is milestones, that is the journey so far. So after the problems with the Adomi Bridge in 2008, a decision was taken to find an alternate bridge to the Adomi Bridge. Therefore, the bridge division, together with survey and design divisions of the Ghana Highway Authority, did a reconnaissance survey to find the possible routes, possible crossings, river crossings. In 2010, there was a pre-feasibility study done by JICA. The feasibility studies considered 13 alternative superstructure types and 4 alternative bridge locations. The 13 alternative superstructure types were 7 of steel and 6 of concrete. In 2013, the phase 2 of the preparatory survey, that is the main feasibility studies, was undertaken. This time, 3 alternative superstructures and 3 alternative bridge locations were considered. The 3 alternative superstructure types considered were 1, a continuous cable-stayed bridge; 2, a precast continuous box girder; and the third one was a precast continuous extra-dose bridge. In 2016, the detailed design survey of the new bridge across the Volta River was undertaken, also by JICA. The continuous cable-stayed bridge was selected because of low construction costs, ease of construction, aesthetics, and low maintenance costs. In 2019, there was the selection of the consultants for the review, for the design review and construction supervision undertaken by GHA. In 2020, there was a design review. The consultants during the design review introduced new technology and materials to enhance quality at lower cost. The revisions were made to the crossbeam format, the inspection parts, that is, using fiber reinforced polymer panels, and then the bridge pavement, that is epoxy resin instead of the asphalt concrete, and a 3D CAD technology to check interference of the reinforcing bars of the main tower with the reinforcement of the anchorage sections. Here we have the project site. First, on the left, we have the eastern corridor stretching from Tema up to Kudungugu. And on the right, we have the link roads to the bridge approaches. The first is from Asuchwari Junction to Volivo, a distance of about 28.3 kilometers. And then from Tufo Adidome to Asikuma Junction, a distance of 38.4 kilometers. A separate contract for the construction of the link road will be financed by the African Development Bank. This is the general view and plan of the new bridge. But first, the key features of a cable-stayed bridge. The main structural elements of a cable-stayed bridge are the bridge deck, the piers, the towers, and the stays. The deck supports the loads and transfers them to the stays and to the piers through bending and compression. So for this, we have 2 towers, 2 set of short piers, and then 2 abutments. This is the front view of the tower. The height from the deck to the crown of the tower is 51.6 meters, and then from the foundation to the tower is 76.5. This column type elliptical pier was selected in order to minimize obstruction to river flow. The towers will be constructed in the water 8-meter deep waters, and a single steel ship pipe coffer dam will be installed in order to construct the piers. The footing will be installed in the rock below the riverbed. The depth of the excavation in rock will be about 1.6 meters. Here we have the piers. the pier front view, that is from Volivo, and then the pier 4 from the Adidoma end. The diameter of the cast-in-place pile is 2,300 millimeters. A 5-meter steel tube pipe of diameter 2,500 millimeters will be driven a minimum of 1.6 into the bedrock. These are the drawings for the abutments at both ends. That is the Volivo and then Dufo Adidome. For this, the diameter of the cast-in-place steel pile is 1,500. The pile foundation was selected in order to secure the safety of the abutments in case scouring occurs on the natural embankment in front of the abutments. This is the cross beams, which are the full web type to be placed at 4-meter intervals. As you can see, the total width of the cross section is 17.1 meters. During the design review, the cross beam was revised in order to save material. So we have the use, the revised cross beams are the truss web format cross beam, which is the one on top. Which is the one on top, which will be for all cross beam locations, excluding the anchorage points for the cables and the piers. With this format, the weight of the steel is reduced, thereby reducing costs. The cable anchorage points will have full web beams with openings for the pathways. This is a summary of the project scope for the bridge works. First, we have the foundation for the abutments, which will be pile foundations. Foundations for the piers, as I said, will be a spread foundation for the towers, which will be in a steel sheet pile cofferdam. The abutments will be a reverse T-type abutments, and then the piers, the column type elliptical piers. The superstructure is for the main girders is a steel deck edge girder. The main towers is from reinforced concrete. As I said, the height is 7.65 from the foundation and 51.5 from the bridge deck. The bridge length is 540 meters. That is 34 plus 96, and the central span is 280 meters, and on the other end, we have 96 plus 34. The pavement is asphalt pavement, but during the design review, there is the proposal to change from asphalt pavement to epoxy resin. Now we have the stay cables, which is the most important members of the cable-stayed bridge. In this case, the stays will be prefabricated and attached to a socket with high fatigue strength. This will eliminate site corrosion protection works. Dampers will be installed at the end of the cables on the tower and on the girder for protection, and then waterproofing of the cables, anchorage, and then cable vibration. The main tower side socket is inserted and anchored to the main tower anchorage. The girder side socket is inserted and anchored to the girder side anchorage, and then the cable is tensioned. The typical cross-section is 17.1 meters. The auxiliary components of the bridge are the bridge bearings, expansion joints, pavements, traffic signs, guard fences, road illumination, and others, navigation aids, and aviation obstacle lights. The summary of the project scope for the approach roads. On the right bank of the river, that is the Volivo end, we have 890 meters of road. On the left bank of the Volta River to Dufo Adidome is 620. The earthworks to the formation of sub-base, pavement, as I said, asphalt concrete, we changed to epoxy resin. The road drainage is side ditches and cross culverts. And these roads will intersect with Asuchuari at the Ime Road, and before Adidome to Volo Road. The typical cross-section has a total width of 12.3 meters. The summary of the project scope for other facilities which will be provided. First, we have two toll plazas at Volivo and 24 Adidome ends. And then we have toll booths and toll gates, administrative office, temporary parking space for overloaded vehicles, and then the axle load scale. There will also be a rec stop, which will be on the 24 Adidome side, a commercial building, parking lots, and access road. This is the sketch of the drawing of the toll gate, where we have the toll booths and the other things. Then this is the project area, showing the toll plazas, the rest stop. Here we have some two runabouts, but instead of the runabouts, we now have separated intersections. It was first proposed to use mobile gondolas as inspection platforms for the bridge. This is the mobile gondola for the for inspection, for the bridge inspection and under the deck. But during the design review, they thought it wise to now change from the mobile gondolas. Our experience with Adomi Bridge is that by the time you get to use them, there will be a problem. Either they cannot move, and therefore they propose to use a permanent inspection platform. The permanent inspection platform will be made from fiber reinforced polymer panels. The advantages of using the polymer panels is that the mobile gondolas will require maintenance of the gondolas, that is greasing, spares, and other things. While for these permanent ones, I think it will be only cleaning. And this permanent inspection platforms allows for easier inspection from under the girder. And then the inspection platforms will be closer to the underside of the deck plates where the damage is likely to occur. The Volivo Bridge will be a bridge of many firsts. It will be the first cable-stayed bridge in Ghana. It will be the first bridge using weathering steel for the main bridge elements. The difference between ordinary steel and weathering steel is in the chemical composition. Ordinary steel, structural steel, is a combination of iron and carbon. Weathering steels have additional alloys made from nickel, chromium, and copper, but it is 50 to 100% more expensive than the ordinary one. The weathering steel compared to the ordinary structural steel provides enhanced mechanical properties and increased resistance to atmospheric corrosion. The steel ruts on the surface to form a protective layer referred to as a patina. It can last up to 120 years with minimal maintenance. An example of a patina, maybe you all know the Statue of Liberty in New York, and you see its color as green. That green is the patina formed from the reaction of the copper with the atmosphere. But in the case of the weathering steel, the color is brown. It will be the first bridge that will be using the 3D CAD technology to check interference for reinforcing bars and other members. In the area where the diagonal cables are anchored to the main tower, in addition to the reinforcing bars of the main tower, reinforcing bars for strengthening the anchorage sections and pre-stressing tendons will be placed densely. The 3D model will be created in advance to check for reinforcing bar interference. Now, the fiber reinforced polymer panels for permanent inspection platform. So as I said, in place of the mobile gondola for inspection, we will use the fiber reinforced polymer panels. These are strong fibers and embedded in a resin matrix. Benefits include short production and installation time, lightweight, long-term cost savings, and corrosion resistance. Another first would be the use of the epoxy resin pavement in place of asphalt pavements. In Japan, epoxy resin pavements have been used for suspension and cable-stayed bridges since 2005, and have shown a high level of reliability compared to the asphalt pavements, which last about 10 years. So here we have what the completed bridge would look like. And if you happen to travel in the night, this is what you see. This bridge was designed by Mr. Makoto Itoi, a renowned Japanese bridge engineer who also designed the Tokyo Gate Bridge. Thanks for your attention.